Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 11, Organic Chemistry 3. Carbohydrates and nucleic acids. Names and structure of monosaccharides. The D and L system. The configuration of naturally occurring triose positive glyceraldehyde is designated as D capital because it gives actually the dextrorotatory effect on monochromatic light, and the configuration of its enantiomer negative levo glyceraldehyde is designated as L. The G and L system came from proposal made in 1906 by a New York University chemist, Rozanov, and it is still used today for this purpose. The monosaccharides, upon degradation, as we see here, degrade, you eliminate one carbon, then you eliminate another one, then you eliminate another one, until you reach the dextrorotatory glyceraldehyde. The chemist found that for this rotatory glyceraldehyde, this OH is on the right hand. Okay? So they kept saying or naming the compounds with the highest or the last secondary OH, okay, as D family when the OH is on the right. All right. Well, here is D-glyceraldehyde, and you can see that it's really dextro. And L-glyceraldehyde, and it is levo. But the configuration doesn't tell you which way of sugar rotates the plane of polarized light when you go to the O family. If we start with the D family glyceraldehyde, then increase one more carbon up, the OH could be right, could be left. As you can see, it is the D family because this one is on the right. It's D family. But erythrose is levorotatory, while threose again is levorotatory. Well, so the D family, now we know it is not it doesn't tell you it's rotating the plane polarized light levo or dextro. Okay, D only indicates that the last secondary alcohol OH is on the right. That's it. All right. Starting with erythrose, we have the two H's on the same side. We increase one more carbon, could be right or left. So we get ribose and arabinose. Again, D. For threose, one right, left. Then when increase on this carbon, well, the aldehyde functionality, and then OH right, and one left. That's called xylose, and then this one is lexose. Let's go one more time. Take the ribose, you increase one here, right or left, and we get allose, altrose. When we have here arabinose, the pentose, increase one more, OH this way, OH that way, we get glucose and mannose. And what is the relation of these sugars to each other, they are diastereomers. They are diastereoisomers. If you would like the mirror image, the enantiomer, we get the L family. Okay, the L family. For the ketosis, okay, it's 1,3-dihydroxyacetone, the first one in this family. There is no chiral center to name D or L. Then the first one actually will be D family, will be erythritolose. OH, right, means that we have D family. Okay, now more, one OH extra will be D-ribulose. On the left side, that's D plus xylulose. And we keep going here again, right and left, and we get D-bisicose and D-fructose. If we start with xylulose, increasing one OH to the right, sorbose, D again, and here we get the D-tagatose. As we mentioned, the relation is diastereomers. However, if they are just the same except in a single carbon, the stereochemistry is a change. Sugar that differ only by stereochemistry at a single carbon are called epimers. For example, mannose and glucose. Right, 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 left, left. So up to these carbon atoms, the configuration are the same. Well, we get in here, this is left and this is right. Well, I call mannose and glucose epimers at C2, carbon number 2. Okay, we number 1 from aldehyde, 1, 2, so they are epimers at C2. What about the relation between glucose and galactose? Do the same in here. We will find that they are differ only on the configuration of carbon 4. So I call them epimers at C4. Reactions of monosaccharides. As we mentioned, the sugar monosaccharides exist as isomers, open structure with cyclic structure, either in the 6-member ring biranose form or 5-member ring furanose form. Because all of these isomers equilibrate rapidly, the relative rates of their individual reactions with various reagents determine the product distribution of a particular transformation. The first reaction we'll talk about epimerization and enediol rearrangement. Under basic condition, the alpha proton to the carbonyl aldehydes or ketones are reversibly removed, forming the enolate. Then it will re-protonated from the media to form again the hydroxycarbonyl. But in this particular step, we have here a planar enolate. This could attack the H from up face or from the bottom face, leading to a mixture of epimers on that carbon. So we get a mixture. We start with glucose treated with basic aqueous medium. After a while, we get a mixture of glucose and mannose. Why is that? Again, because the base will deprotonate this carbon, take this H out, form enolate. Then the enolate will reprotonate once again from the upper face or from the bottom face, leading to epimers. Another base catalyzed side reaction called Enediol rearrangement. Well, in basic condition, this deprotonation will lead to the formation of enolate. What about the protonation on this oxygen will give this enediol? Deprotonation of this oxygen, this OH, okay, deprotonation of this OH will lead to the enolate. Again, the enolate will abstract proton, but this time we will form with a double bond in here. So we transfer glucose to its ketosis, fructose. Starting with the glucose, we find out that D-fructose is forming in the medium. Show all possible reactions of fructose under basic condition. Fructose under basic condition, here is the carbonyl, alpha, acidic hydrogen, base will get this hydrogen to form enolate, then this will come back attacking water molecule H and reprotonation once again from the upper side or from the bottom side, leading to the formation of again epimers in here on this carbon. Here is OH of fructose left. We get a mixture of left and as well as on the right. So we have this plus this. What else? Okay, we have the enolate, protonation of this oxygen, then abstraction of hydrogen from this. Once again, goes back, deprotonation from upper face or the bottom face, will give mixture of OH to the right and left, and moving of the carbonyl from carbon 2 to carbon 3. So we will get mixture of this plus this plus this. Reduction of monosaccharides. We know monosaccharides exist in cyclic and open structure. In the open structure, we have an aldehydic functionality with or ketonic in the ketose, which could be reduced easily with sodium borohydride or nickel hydrogen and nickel as a catalyst to give what we call alditol. So glucose will reduce in its open structure to glycetol or sorbitol. On the other hand, the fructose, D-fructose, will be reduced by sodium borohydride to a mixture of glycitol and mannitol. Okay, here we have ketonic function, can be reduced either OH on that way or on the other, on the left hand side. When glucose is reduced with sodium borohydride, optically active glycitol results. When optically active D-galactose is reduced, however, the product is optically inactive. Explain this loss of optical activity. D-glucose with sodium borohydride, you reduce this carbonyl aldehydic functionality to CH2OH. And the molecules, as we can see clearly, does not have any kind of symmetry. So glycitol is optically active molecule. In case of galactose, OH right, left, left, and right. Now with sodium borohydride, again, you reduce the aldehydic functionality to CH2OH. Yeah, it's clearly that this molecule have an internal mirror image. So it is mesoform, meso configuration, and D-galactitol will be optically inactive. Amer Fischer synthesized L-gallose, an unusual aldohexose that reduces to give D-galactitol. Suggest the structure of this L-sugar and show how L-gallose gives the same alditol as glucose. When we start with glucose reduced with sodium borohydride, you form, again, transfer this to CH2OH. We are talking about L-sugar. So if we look at this OH on the right, if we move this molecule 180 degree on the plane of the paper, then we get the OH on that side, right? And this one will be on the other side. And these two are the same side as the OH. So they will be on the left. Now, looking for this kind of L type, we take this backward to the aldose structure, so transfer it to aldehyde. This is an L sugar, and that is the L gallose. See you next lecture.